Let's take a look at Mohrs strain circle. Okay, we will see that the stress transformation Mohrs circle is very similar to Mohrs circle for strain. On the x-axis, we have normal strain, similar to stress. We have normal stress. And on the vertical axis or y-axis, we have the shear strain in place of shear stress. The minor difference is that the shear strain is half or divided by 2. That is the only difference in between the two circles for stress and strains. The equations we have seen before is very similar and the only difference again we have seen is for the strain value. We have half shear strain in the equation. The radius is still the same. The radius is equal to the maximum in plane shear strain, but in this case is half. Half the in plane maximum shear strain, that is R. How we are going to draw it is very similar, although not exactly the same. First, we establish the coordinate system and we determine whether the vertical axis gamma over 2 is going to be in the left, on the left, or somewhere in the middle or to the right. So it depends on the value of the normal strains. If both the normal strains are positive, then the shear strain axis is to the left of your diagram. Okay. If one of the normal strain is positive and the other one is negative, then the vertical axis is somewhere in the middle. And if both of the normal strains are negative, then the vertical axis is to the right of the sketch. Or if you draw graph using graph paper, then you put it exactly on the paper. And positive shear strain is downwards in the graph. So first we determine the center of the circle, and that is the location of the average normal strain. Okay, so we determine C. And average normal strain is very easy to find if you know both strain X and strain Y. Then we plot point A as mentioned in Hibbeler, or if you use other text, maybe they will call it point X, right? So point X will have a coordinate of strain X and gamma over 2 XY. So we plot that point first. After knowing C, we plot that point and we can join point C and point X or A. Okay, and that line is the location of our primary direction, which is X. If we have these 2 points, we can then just extend that point to get point B or point Y, right? And coordinate for Y is strain Y and gamma XY over 2, but it is negative because it is clockwise rotation of the sides. Right? And then we can draw the circle or you can sketch the circle. If you have drawing tools, you draw a circle. Otherwise, you just sketch a circle or something that looks like a circle as your reference. Principal strain occurs at point B here and at point D. So point B is the maximum normal strain and point D is the minimum normal strain, or in other texts written as strain 1 and strain 2, right? And since point A or point X is our reference, that is the primary direction of x-axis, to go to principal 1 or principal strain maximum normal strain, we go counterclockwise from X or from A. So we go counterclockwise, so that's 2 theta P1. So if we go 2 theta P1 counterclockwise in the real world, we have X as our reference. We go counterclockwise, but the angle is theta P1, right? And that goes to X prime. And so our strain element will be on that axis, where here is y prime. Okay. When both strain 1 and strain 2 are positive, then both sides will elongate as shown in figure B. So we have elongation. So is over here is strain 1 dx prime. And over here, the elongation is strain 2 dy prime. Okay. The maximum in-plane shear strain is given by the radius itself, and the location is given by point E. So we can find 2 theta s from A. So we have 2 theta s is going clockwise, right? So in the real world, it is just theta s clockwise. And from that, we can get our undeformed square or rectangle for our strain element. And in this case, we have both normal strain, where the normal strain is equal to average normal strain, and also we have shear strain. If the average normal strain is positive, then we find that both sides it is an elongation. So we draw an elongation, right? And we draw a straight line over there. We just draw a straight line first and another straight line at point Y. So we have that straight line there. You can just draw a straight line. And then we put in the shear. Now on the X prime axis here, on that axis we have down here, the shear strain is positive, is gamma over 2 and is positive. So when it's positive, it is getting inside, or the angle gets smaller. So when the angle gets smaller, that angle there is gamma max over 2. Okay, and similarly over here, that angle there is gamma max over 2, and it's in plane. Okay, so we just draw two lines from point O, the reference. So we just draw two lines which shows that they are positive, gamma max over 2. Okay, when they intersect the first line for normal strain on both sides, then we draw parallel lines to the first one. So this line here is parallel to this line, while this line here is parallel to this line. Okay, and that's how we get the deformed element. Now if we want to find strain on any arbitrary plane, meaning just any x prime and y prime, so we just draw the angle. Okay, so let's say that angle is 2 theta and it is positive, so it's counterclockwise from x, so that is our x reference. So we just draw counterclockwise 2 theta, okay, where the origin angle is theta. That will give us a radial line CP, and if we extend to the left is CQ. The angle here is 180 degrees, right? 180 degrees, and the actual angle is 90 degrees. Okay, the actual angle is, and the element is given by the dotted lines. The broken lines will show you the actual strain element before deformation. Now to find the deformation on the x prime, we just find the coordinates for point P, and on the y prime we find the coordinate of point Q. So finding this coordinate should be easy using geometry. An example here, as an example, we have the state of plane strain at a point is represented by the components. Strain normal x is 250 microns, strain normal y is negative 150 microns, and the shear strain is 120 microns. Determine the principal strains and orientation of the element. So we can just sketch more circle. First we plot the centroid. Okay, the centroid. So we find here that the normal strains, the x value normal strain is positive 250 and the y normal strain is negative 150, about half the value of strain x. Okay, epsilon x is more to the right and epsilon y is to the left. So we make sure that our vertical axis, that is axis for for shear strain over 2, is towards the center, not exactly at the center of our graph paper, but close to the center, okay, about 1/3 of the way. Then we plot point C. Point C is the centroid and it is between strain X and strain Y. So we find the average value 250 plus strain Y minus 150, so is 100 divided by 2. So we have 50 microns, right? So that gives us point C. Then we plot point X or point A. So we can call that X even. So epsilon X is 250. So we plot epsilon X 250. And we plot gamma xy over 2. So that's half. So it's 60, right? So we have 60 and it's positive, so it's downwards. So that is 60 microns. Okay. And where they intersect, we will have the first point. Then you join that point with C to get the straight line. Okay. And that straight line is the location of x-axis or the surface which is parallel to the x-axis. Okay. So our coordinate here will be 250 and 60. And if you wish, we can extend it to the left for the y-axis, right? But don't bother about that one at this stage. So our purpose is to find the principal strains and the orientation of the element. So the principal strain will be given by point B here, and the coordinate is epsilon 1, 0. And the principal 2 or minimum normal strain is given by point D, where the coordinate is negative epsilon 2, 0. So let's take a look at point B, and the plane BC represents the location of the principal plane for epsilon 1. And we can calculate, or we can measure from the graph this angle here, 2 theta P1. And it is counterclockwise from X. So if we calculate that value, we can find that theta P1 is 8.35 degrees. It's a very small value. And epsilon 1 is 259 microns. Epsilon 2 is minus 159 microns. So if we plot, or if we sketch the strain element, we can find figure B on the left. Our primary direction is X, right? So that is primary direction. From X, we take counterclockwise half the angle, so it's 8.35. It's positive to get to X prime. The blue square or rectangle is our reference undeformed strain element. And we see that strain 1 is positive, so it's an elongation. The elongation is given by strain 1 dx prime. And strain 2 is negative, therefore it is a contraction. It gets shorter on this side, and the value is strain 2 dy prime. So we just complete the rectangle with the broken lines.